Ladies and gentlemen, welcome to Engineering Dynamics. In this video, we will continue with the mode superposition, but this time we will probably covering the most important topic, and that is resonance and the forced harmonic response. Let's jump right in. We have a linear system and we have an additional force that is acting with a cosine. So we have a set of amplitudes, so that is our vector of amplitudes, and we have a excitation frequency. So for example, if you have a system, let's get rid of this. If you have a system that has 2 degrees of freedom, we will have a vector that will have 2 amplitudes, say A and B, times cosine omega t. So we're exciting both degrees of freedom with one excitation frequency. So we know that if we have this kind of excitation frequency, that our solution has to also have a cosine, because if you derive a cosine once and a cosine twice, you will get again a cosine. So you have a cosine here, a cosine there, and a cosine here. So this will be our solutions. The only thing that we need right now is to solve for the x. So let's insert our solutions that we had here into our linear equations of motion. We will get we will get k times x cosine minus m times x cosine omega squared plus s cosine. We can get rid of the cosine here, here, and here, and we are only left with kx minus omega mx equals s. So now, if we know the amplitude of our excitation vector and we know those matrices, we also know the omega, we can solve this system because this is a fixed matrix. There is no variable. There's just a matrix that is A times B is equal to X, and we can get B by just pre-multiplying A minus 1 times X, because this matrix is invertible. So again, this can be solved by inverting. But as soon as we have a system that has millions of degrees of freedom, this matrix will be a 1 million by 1 million matrix. And inverting a matrix this size is very, very inefficient. So it will take millions of iterations to solve that matrix. And as soon as we change our excitation frequency, we have to solve it again and again and again. And we don't want the solution only for one excitation frequency to get the x, but we want it for multiple excitation frequencies. So solving it by inverting is not what we want to do. So we want to get x, but we want to use the m and k orthogonality again. So we define our x as a eigenmode series expansion. Just like we had before, we have a sum of our eigenmodes and the time function, but this time we also consider the rigid body modes. So these are our u's, and this is the function for our rigid body modes. So inserting this equation into our linear set of, where is it? Right there. Inserting it in this equation will get us this equation. Now we use the m and k orthogonality. We pre-multiply with xr. So we're left with, this is gone because this is not an x, and we are left with x r pre-multiplied k minus omega x r transposed m, and here the sum is gone and the s turns into a k. And of course, if we pre-multiply on the left, we also have to pre-multiply on the right. Then we put our x into the brackets, so we are left with xkx, and omega xkm times eta is again our pre-multiplied amplitude, and this will turn into our modal stiffness. This will turn into our modal mass, and we again have the uncoupled equation. So if we want to solve now for eta, we divide this by this, and we will get this equation. for our eta r. But of course, we have the modal mass here and the modal stiffness, and we want to simplify it even further. So we can use our Rayleigh coefficient, Rayleigh quotient, and we know that our gamma is omega times mu. So eta is our eigenfrequency minus our excitation frequency. And here we are missing a square. So we know now our eta r. But now we have to also consider the rigid body modes. So if we pre-multiply with a rigid body mode, this is gone because we have elastic modes here, and we are left with this times this times this. But we have to remember that rigid body modes, UK, is equal to 0 because K is our stiffness matrix, and if we have a rigid body mode, we're not activating any stiffness. That's why we have 0 elastic forces. This is why K is also gone. We are left with U omega squared m times xc u and U transposed S, because if we pre-multiply on the left, we again have to pre-multiply on the right. So we have our xc omega. This, and this will turn into our modal mass. The right side stays the same. And if we want to solve for xc, we just divide this part by, oh, sorry for that. Let's remove that, by this one, and we get this equation. So what we are left with is this one and this one. So if you understand that, that is already very, very good. So now we have the solution in a physical space that is a sum of our rigid body modes with our time function and the elastic modes with our time function eta. So let's insert that now. We have a x that is, oh, sorry, we missed a minus because we have a minus here, we have a minus there, and also here. So we have a, don't forget this minus. So we are left with this function because we inserted our etas and our x's. So what is that function? So if we look at our solution, what we actually did is we inverted our mass matrix. So by having this part here, this is basically just a algebraic inversion of our mass, so of our matrix. So we don't have to invert it with iterations, but we can just calculate the inverted matrix with the help of those eigenmodes and eigenfrequencies. So by doing a little bit work up front, that is calculating the eigenmodes and eigenfrequencies, we save a lot of work later, or we can actually do work that would be impossible to do if we didn't do the work up front. So by getting this equation, we can now invert this matrix. And now we can talk about the actual frequency response function. So what is the response of degree of freedom k if the harmonic excitation is acting on our degree of freedom? So for example, if we have a double pendulum and I apply a harmonic excitation on the first degree of freedom, how will the first degree of freedom change and how will the second degree of freedom change? And we do that by only looking at one part of our vector. So if we, for example, apply a force, a force on J, on degree of freedom J, and we will look at the response at the amplitude of degree of freedom J. So this will be our AJJ. Then we again just use our function. So we insert our function here. So this is basically, we put this right there. So we're only left with this part. So we have this function where we look only, this J means that we only look at the jth element. So if we have a vector that has something J, something, something, we only look at this part. So of the ith of rigid body mode number I, we take the element j divided by the modal mass of modal I. Here we have the element j of our elastic body mode of mode S, eigenfrequency of S, and the excitation frequency, and again the modal mass of S. So what we see that will happen is that if we are close, so that omega is approximately omega squared, so if these two are almost the same, this term will explode and we will have a gigantic amplitude. So even if we have a very, very slight excitation at the right frequency, the system will fall into resonance and the amplitude will rise with the frequency. With frequency. So let's look at a special property of that response function, and that if we derive with our excitation frequency, we see that the amplitude is always increasing. So that the amplitude is always increasing with the excitation frequency. So if we have a system and we start exciting it, the amplitude will always go up. So if we excite it with a frequency of 10, we will have a certain amplitude. If we have a frequency of 20, it will have a larger amplitude. But what does it actually mean? So here we have this frequency response function graph. We start at a fixed point, and that point is because we have rigid body modes, and our frequency response goes up, 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 till the point where we hit our first resonance, so where the excitation frequency is equal to the eigenfrequency. But then we are by an infinity, but we can't go higher than infinity, so it actually jumps back down, and we start at minus infinity, and we go again up, 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 till we hit the second eigenfrequency. And this will go on till we hit every single eigenfrequency, and then it will go to 0. So you will have graphs, if you have many degrees of freedom, that will look, sorry, that was ugly, that will look like this. So they go always up, up, up. And you see that we have special points, and those points, we call them anti-resonance. So again, if we have our example with the double pendulum, there is a special frequency where I can excite 1 degree of freedom with just the right frequency, that the degree of freedom that I actually excite will not move, and only the other degree of freedom will move. So these points are actually the eigenfrequency of the system where 1 degree of freedom is fixed and we're only looking at the other degree of freedom. So the most important part that you have to remember is that there are points where I can excite a system, but I will get no response back at this specific point. So consider that we are only looking at one point. Let's summarize the whole thing again, because this is very important. We had a system and we have a excitation. Then we propose a solution, derive it twice, and insert it into our equation. We could solve that system by inverting, but we don't want to because it's very complicated. Then we have the expansion of our eigenmode series. So we have the solution and we can expand it with those rigid body modes and elastic body modes, because they form a basis that they serve as a basis that can be used to describe this X. Then we insert our solution, and in the equation that we had, we use M and K orthogonality. In this case, we pre-multiply with XR to get our eta that we will use like this. And then we pre-multiply with our rigid body mode and we get our Xi. So then we insert it into our solution, and what we get is a function that can help us to invert these large matrices that we had before. So instead of inverting a 100 by 100 system, we just have 100 eigenmodes that we just stack together, and this will be way easier than iteratively inverting the matrix. Then if we look at the frequency response of 1 degree of freedom, if we excite that degree of freedom, we see that we get a frequency response where the amplitude is always increasing. And we will get a graph like this, where we start from a point because of our free rigid body modes, and we will come closer to the eigenfrequency where the amplitude is infinity. Then we fall back and again start from 0, cross the anti-resonance, and continue to the next eigenfrequency. If we have a system with only 1 degree of freedom, we will not have a anti-resonance, because if we have 1 degree of freedom, we start from here and we go again to 0. So only if we have 2 degrees of freedom, we will have 1 anti-resonance. I hope this video gave you a better understanding about the frequency response function. I know that this is a very, very difficult topic, and if you have any questions, please watch the video about where we do an exercise to this topic. And if you have any questions, feel free to ask them in the comments down below, and I'll see you next time.